Good morning, everybody. So, without many more words, I just call Professor Bill Phillips, please.
Okay. So, for those of you who were at my presentation last night, if you thought you were going to get a similarly entertaining talk this morning, boy, are you going to be disappointed. Most of these talks are things that we think Dan will be interested in scientifically, and I'm going to be talking about synthetic electromagnetic fields for cold neutral atoms. And I want to emphasize here are the people who have worked on the things I'm going to be telling you about. Ian Spielman of my group back at NIST and the Joint Quantum Institute has been the leading engine behind this work. Trey Porto is a senior colleague who's been part of this as well, and all these wonderful young people have been part of that. This here's a picture of the young people. This is Karina Jimenez Garcia. This is Ian Spielman, the leader. Yuju Lin, who is as a postdoc has done a tremendous amount of this work. Rob Compton, Lindsay LeBlanc, who's been involved in the more recent work, along with Abigail Perry and Ross Williams. Matt Beeler's just joined us in this effort, and Trey Porto is the senior colleague that I was mentioning to you. There's another main player in this, and that's rubidium. This is all done with a Bose-Einstein condensate of rubidium, and of course, last night we talked about how Dan's contribution to Bose-Einstein condensation has been so important. And okay, so what is this all about? Well, quantum degenerate gases, Bose-Einstein condensates to begin with, and later quantum degenerate Fermi gases, have opened up all sorts of new research directions. And among those research directions is simulating interesting problems, interesting Hamiltonians that often have their origins in condensed matter physics. And all sorts of wonderful things have happened. So among them have been things like looking at the Mott insulator transition. So just to briefly say something about that, if you have a lattice on which particles, like say electrons, can move freely, then there can be a phase transition that happens at zero temperature between a situation where those particles are moving freely as a superfluid or as a superconductor, for example, or as a conductor in an ordinary metal, and a state where they are stuck to their individual lattice sites as an insulator. And that Mott insulator transition is something that defines a great deal about the difference between insulators and conductors, metals or superconductors in condensed matter physics, but it's very difficult to see the actual transition occur. Whereas in cold atoms, it's been easy to see that transition occur, and it was one of the first great triumphs of quantum simulation that happened at the Max Planck Institute for Quantum Optics in Garching. The BCS-BEC crossover is something that was predicted for a long time, where pairs of particles could pair up as Cooper pairs and form a superconductor or a superfluid, and they could also pair up as molecules that are then bosons and could Bose condense. And that transition is seen explicitly in condensed matter systems, but not something that's something that you can see in condensed matter systems. But in atomic gas systems, it's been seen. Block oscillations, something predicted many years ago by Bloch, the idea that if you have electrons moving in a lattice, it's a conductor. You apply an electric field. The electrons move. They accelerate. They accelerate until they get to a velocity such that they satisfy the condition for Bragg scattering from the lattice. They Bragg scatter from the lattice and reverse their velocity. They continue to accelerate until they reach the Bragg scattering condition again, and then they reverse their velocity. And this is responsible for the well-known phenomenon that conductors do not conduct electricity. But of course, conductors do conduct electricity, and the reason that they do is because there are imperfections in the lattices. The electrons scatter off the lattice imperfections, they scatter off phonons, and so you don't see this phenomena typically in condensed matter systems. But it's easy to see in atomic gas systems. So these are some of the things that have been done using quantum degenerate atomic gases in the way of quantum simulation. But there's a problem. If you want to simulate some of the important things that are done, that are interesting in condensed matter physics, and that is that in condensed matter physics, one often is dealing with electrons, and electrons are charged, whereas neutral atoms are not charged. So how do you deal with the influence of fields on these particles? A lot of times it doesn't matter. A lot of times there is screening of the electric fields, and it doesn't matter very much, but sometimes it does. Well, it's been easy, for example, to simulate the behavior of electrons under the influence of an external field, just a uniform acceleration. We just accelerate the lattice instead of applying a force to the electrons. That works very well. But what if you want to simulate the Lorentz force? What if you want to simulate the effect of a magnetic field on a moving charged particle, V cross B? How do you do that? Well, one approach has been to rotate the system. If you rotate the system, you know that if you go into the rotating frame, then you'll have a centrifugal force and a Coriolis force. And the thing that I want to draw attention to is the Coriolis force. It has the form V cross omega. So that if you think of the rotation as taking the place of the magnetic field, then in the rotating frame you have something that has the general form of a Lorentz force, and the rotation has the effect of being the charge, an effective charge times an effective magnetic field. Now this is wonderful, and people have done wonderful experiments with rotating traps. Vortices come into the traps, but there are problems. It's very difficult to get the rotation velocity high enough so that interesting magnitudes of effective magnetic fields can be reached. And I don't want to belabor this point too long. Some of the people in the audience have been the heroes of rotating systems and found, I'm referring to Eric Cornell, that that there are problems, and he's spent hours explaining to me what the nature of some of these problems are. A very simple one is that in order to rotate the trap, it has to be asymmetric, and as you rotate it, you have a centrifugal force, which is going to make the trap go unstable in one direction before it goes unstable in the other direction. But there are far more difficult problems, both difficult to deal with and difficult to understand, that Eric has explained to me. So what do you do? And the answer is you take a different approach. Let's remember how we think about magnetic fields in quantum mechanics. If we have a free particle, its Hamiltonian is just p squared over 2m. If we have a charged particle in a magnetic field, one of the ways we deal with this in quantum mechanics is to add a term to the Hamiltonian, actually to the momentum, the charge of the particle times the magnetic vector potential. So this is the Hamiltonian for an otherwise free particle, a charged particle moving in the presence of a magnetic vector potential. Now the momentum here, the p, is the canonical momentum. It's the momentum that's canonically conjugate to the position. It is not the mechanical momentum. It is not the mass times the velocity. In fact, the mass times the velocity is the thing that's in this, the parentheses. So what does this mean? It means that I now have a dispersion curve that is, instead of being the classic p squared over 2m that has its minimum at p equals 0, is p minus qa squared over 2m, and it has its minimum at qa. So what this is telling me is that if I want to simulate the presence of a magnetic vector potential for a particle that is otherwise uncharged and would otherwise be unaffected by magnetic fields, I can do that by shifting the dispersion curve. So how am I going to shift the dispersion curve? Well, the answer is always the same in our laboratory, and that is we do it with light. We're going to use laser beams to couple together two nearly degenerate ground states of the atom, rubidium in this case. So we're going to have a Raman coupling between one ground state where we take that ground state up to some virtual excited state, close to the real excited state, with one of the laser beams, and drive it back down in a stimulated fashion to the other ground state. Now, a number of people over the years have come up with schemes for how this would allow you to create a synthetic magnetic field. But Ian Spielman in 2009 published a different approach, which I'm going to be telling you about now, which has been the one that has been successful in making all of this happen. So there's Ian Spielman. So here's the idea. Very schematically, where I'm simplifying the energy structure of the atoms that we're dealing with. So imagine that I've got an atom that has two electronic ground states that can be coupled by these lasers. And what I'm going to draw now is the energy diagram in the dressed atom picture. In the dressed atom picture, I hope most of you are familiar with that, but if you're not, what it means is that I take into account the energy not only of the atom, but the energy of the photons, and eventually, although not in this diagram, but in the next one, I'm going to also put in the energy of coupling between the light and the atoms. But in this one, I'm just adding up the energy of the atoms and the energy of the photons and putting them all together. So on this one, we have the energy of the plus state, plus the energy of n photons from the red beam and n photons from the blue beam, and it has some energy, and it has the typical dispersion curve. And over here, remember, this axis here is momentum. Over here, I have the energy of an atom in the minus state with n plus 1 red photons and n minus 1 blue photons. Now, why do I do that? Because in order to go from this state, the plus state, to the minus state, I absorb a blue photon, so I have one less blue photon, and I emit a red photon, so I have one more red photon. Okay? And why have I drawn the curve over here? Because in doing that, I change the momentum of the atom by the momentum of these two photons. So let me describe how that might go. If I have an atom in the plus 1 state, and let's say that it is moving to the left, that puts it on this part of the curve. So let's say it's moving with a momentum like this. That momentum is the momentum of a single photon. It absorbs a photon from the blue beam. That gives it a kick to the right. It emits a photon into the red beam. That gives it another kick to the right. So it's now been given two kicks to the right. That means it's now on this curve, and it's on this branch of this curve, and that's an atom moving to the right with the momentum of one photon. So that's where these diagrams come from. But as everyone knows, in quantum mechanics, when we have two curves that cross here, that's where the degeneracy is. If there's anything that couples those two curves, they will not cross, but they will anti-cross. And of course, there is something that couples those two curves. It's the light. The atom can absorb from the light and go from one state to the other, so they're coupled. And when we turn on that coupling, then we see that there's a splitting, and in fact I've drawn this with a very big splitting because that's the situation that we encounter in the lab. And the important point to note here is that these new states, these new dress states, look, at least at the bottom of their this new dispersion curve, like a harmonic dispersion curve with a different effective mass and with a minimum at a place that it doesn't correspond to the minimum of the other dispersion curves. So that's what we're going to work with in order to manipulate the dispersion curves in the way we want. Now, if I change the detuning of the laser beams, see in this case, the detuning was exactly on Raman resonance. That is, the difference between this frequency and this frequency is exactly the difference between these two curves, and that's why the bottoms of these two curves are have the identical energy, because everything is on resonance. And the amount of energy that you lose or gain by taking photons in and out of the field is exactly equal to the difference in the energy between the two states. But what if that is not the case? What if you have a different tuning of the lasers? Then you can see that this energy curve is raised compared to that one because I've changed the amount of energy in the blue photon. I've given more energy in the blue photon, and I've given up an extra blue photon. But anyway, you see, the point is that that I've shifted where the dispersion curve is, and this is the whole point. By changing the detuning, I can shift where the minimum of the dispersion curve is, and that's like shifting how big the vector potential is. If I make that change in space in the right way, so that the vector potential has a curl, then I've got a magnetic field. That's the whole story. Okay, so I've given away the plot line of this lecture. So now all I have to do is fill in the details. So here's the real atom, rubidium. It has 3 electronic ground states in the F = 1 level, and they're nearly, that is, their spacings are nearly degenerate. There's a slight difference in the spacing because the Zeeman effect isn't completely perfectly linear, but to a first approximation, they're coupled in pretty much the same way by all of these Raman lasers, which are coming from opposite directions, just like in the previous picture. And when I do all my couplings, these thin black lines are the dispersion curves in the absence of the lasers, and these thick red lines are the dress states. And when I'm on resonance, I have a new dress state whose minimum is at 0, just like the minimum of the M = 0 state of rubidium. But when I change the detuning, I shift where that minimum is. And now we're going to see what the effect is of having that kind of shifted minimum. So here's the experimental setup again. We have beams coming from either side. We have a real magnetic field, which has nothing to do with the synthetic magnetic field we're trying to create. The only thing it does is create the energy difference between the electronic ground states. We're going to create, as a result, a synthetic vector potential, and that vector potential is always in the direction of the laser beams, because it's the laser beams that provide the momentum. Remember that vector potential times charge has the units of momentum. So it's all about the momentum, and the momentum is transferred in the direction of those laser beams. So that's the direction of the synthetic field. And when we produce a gradient of the physical field, that means we have a gradient of the detuning of the light, because we've changed the spacing of the energy levels, and that will give us a synthetic magnetic field, because that gradient of the detuning produces a curl in the synthetic A field, and that's going to give us a synthetic B field. Okay, so again, here's the dressed states. Now, how do we tell what we're doing? In our lab, the answer is always the same. We turn off all the fields, and we let the atoms go. They go wherever they go by time of flight, and then we take a picture of where they are. That's always how we analyze these things. And what's going to happen is that this dress state is composed of the other bare states. It's composed of the M = 0 state with a momentum 0. It's composed of the +1 state with a momentum of -1 photon, because it's on this branch. It's composed of the minus state with a momentum of +1 photon. And so when we release all of the fields and take a picture of where the atoms are, the ones with different momentum fly in different directions. The one with different M states are affected by a gradient magnetic field, which we put on, a kind of Stern-Gerlach field, to separate out the M states, and those are separated in this direction. So here are the 3 components that I described to you before. So this is how we tell what we're doing. Now, this is what happens when we change the detuning a little bit. The momentum of the different components of the wave function of the atom are shifted, because we've shifted where the minimum of the of the dispersion curve is. And that shift tells us how big the vector potential is. The vector potential is simply a measure of how far we've moved the minimum of the dispersion curve. So here you can see where that dispersion curve is, and you can see a little bit better what the composition is likely to be. It's going to have some of this state and some of this state and a lot less of this state, and indeed that's exactly what happens. You see that it has some of that state, some of that state, and very little of that one. Okay, so there's the picture again, and then we just do this for a lot of different values of the detuning of the from resonance, from Raman resonance. We plot out a curve like this, which is the measured synthetic vector potential as a function of the detuning, and this just reminds you what the dispersion curves look like approximately at different places in this map of what the vector potential is. Now we're ready to get serious and make this vector potential do something interesting for us, because after all, a uniform vector potential is pretty boring. A uniform vector potential is nothing, right? A uniform, if it doesn't change in time and it doesn't change in space, it doesn't do anything. So now we're going to make it change in space. We're going to give it a curl, and then that will be the same as a synthetic magnetic field. So we give it a curl, as I've told you, by making a gradient of the magnetic field in this direction, and that's easy. We've got coils of wires. We can make a gradient of the magnetic field, and so instead now of thinking of this curve as being vector potential versus detuning, we can now think of it as vector potential versus the position in the y direction, where the y direction was this direction, and x is the direction in which the laser beams are, and z is the direction in which the synthetic magnetic field is going to be. So this means that this is the form of the vector potential. It's some constant, which I'm calling b for obvious reasons, times y, because it's a linear gradient, and this curve, at least in this part, is linearly, the vector potential is linearly related to the y position, and it's 0 in the other component. So the x component of the vector potential is b times y, and the other components are 0. If you take the curl of that, you get a magnetic field in the z direction. This is called the Landau gauge. So we do that. We put on the vector potential, that is, we put on the gradient magnetic field to have a gradient in the detuning, and this is a series of pictures taken of the cloud of Bose-Einstein condensate that has been released from the trap after this process has happened. We turn on the synthetic field, we let it equilibrate for half a second, and this is the picture you get for various values of the gradient of the field. So when there's no field, you just get your ordinary Bose-Einstein condensate, featureless. When there's a little bit of field, it distorts it a little bit. Why does it distort it? Because when you turn it off, there's a time dependence of the vector potential, and a time dependence of the vector potential is what you do to get an electric field, and the electric field is different at different places because there's a gradient of the A field, so there's a shear on the cloud which causes this shape to change. But when you make the synthetic magnetic field big enough, you start to get these dark spots, and those dark spots are the cores of vortices. These vortices are entering the cloud because the cloud is responding in just the same way that a cloud of conductor or superconductor would respond if you put a magnetic field on it. It would try to shield out the flux by having vortices enter. And there's a threshold for the vortices to enter, which at first we didn't understand, but then we read Sandy Federer's papers, and then we understood why there should be a threshold. And so at some threshold value, which is bigger than the amount of magnetic field that corresponds to one flux quantum in this region, we start to get the vortices enter, and you get more and more vortices enter as you make the synthetic field bigger and bigger. So that's just what you'd expect. If you wait, if you let the system sit for longer than a half a second, then very slowly the vortices disappear. If you wait for less than half a second, the vortices haven't yet gotten a chance to get in. The vortices are sort of coming in from the vacuum, and they penetrate the edges. And here, you don't really see much of anything. Here you see the vortices sort of nibbling at the edges of the cloud. And as you wait longer, they've all gotten in, and as you wait longer still, they go away. Why do they go away? Because the atoms are going away, and the atom cloud supports a certain amount of flux entry, and as the area gets smaller, as the number of atoms gets smaller, then the number of vortices that will fit in there becomes smaller as well, and all of this is just as we expect. Okay, and amazingly, I've come to the end of my talk at the right time. So here are the conclusions. The conclusions are, this is wonderful, and that's all I have to say. Thank you very much.
Bill, I'm fairly confident I've asked you this question before, but I forgot the answer, so I'm
Right.
going to ask it again. So we have a Coriolis force.
Right.
Is there also a centrifugal force?
Yeah. So the answer to that is that I don't know for sure, because I've asked myself that question as well. So when I ask other people this question, they assure me that it is, but I'm not quite sure I see where it's coming in. So I don't know. Sorry. But if there are any theorists in the audience, I would be happy to listen to your opinions about whether there is effectively a centrifugal force here. Even if there are some experimentalists who think they know the answer, I'd be happy to hear that too.
Hi. Yeah, it's a wonderful work, I mean. But let me ask you, do you think it's possible to simulate non-abelian gauge fields?
Yes, but not quite so easily. So the question is, can I make a non-abelian gauge field? And the answer is yes, but it's not quite so straightforward. But I see Sandy's hand up, so maybe we'll get a more cogent answer.
Well, what I wanted to ask is, why don't they eventually form a regular array?
Yeah.
Is it just because it's not long enough time?
Yeah, so Sandy's question is, I was hoping he was going to answer your question. So let me just continue answering that, and then I'll answer Sandy's question. So the answer is, in order to get a non-abelian, you've got to do something funny with the interactions. And so there are some ideas for how to do that. And so when you've got somebody like Paul Julian around, you can figure out how to make the interactions funny. So that's one approach to making a non-abelian gauge field, is to have funny interactions. Now, Sandy's question was, why don't they form a regular lattice? Let's go back to the picture that doesn't have the regular lattice. So you look at this and you say, why isn't this? Because those vortices are repelling each other, and they should form a triangular lattice because that's the minimum energy configuration. But they have to equilibrate. And there's the problem. That's why they're not forming a regular lattice. But if you use your imagination, you might be able to think that they're starting to try to form a regular lattice here, but it's not quite there. And the reason is we just haven't waited long enough. And this actually is a real problem, because we can't wait longer. You saw in the next slide, if we wait longer, the atoms go away. Now, why is this? The reason is that we've got light shining on the atoms, and all I told you about was the stimulated process, where the atom absorbs a photon and is stimulated to emit. But sometimes it absorbs and there's a spontaneous emission. That's bad, because the spontaneous emission transfers so much momentum in a random direction that the atoms leave the condensate, and that's how we lose atoms. So then you say, but why don't you just detune your lasers further from resonance? And the answer is that when we detune the lasers further from resonance, the usual thing when you're getting too much absorption in these experiments is you detune the lasers further from resonance and crank up the intensity so that you get the same amount of Raman coupling. But there's a problem. And the problem is that the coupling that we have, which changes the M value of the atoms by 2, is going away as we detune further from resonance. So that as we detune further from resonance and crank up the intensity, we we don't change the ratio between the spontaneous emission and the size of the Raman coupling. See, if all that we were talking about was light shift, if this was just a trap, then we would tune further from resonance, we'd crank up the intensity, and the ratio of the trapping force to the spontaneous emission rate would go up. We'd be better off. But we can't do that because this Raman coupling has a dependence on detuning, which is the bad one. And so Ian Spielman is coming up with some clever ideas to fix that.
Bill, I have a question, and I'd like two answers to it.
A right one and a wrong one?
No. How big is the largest field you can actually synthesize here?
Yeah.
And the answers I want are in Gauss, because that's what I use.
Right.
And, of course, in Ørsted, because that's what you're legally required to use.
No, as a matter of fact, I'm legally required only to talk about Tesla. I cannot deal in Gauss or Ørsted. It's against the law
I see.
for somebody from NIST to talk about anything but Tesla. In fact, you'll notice that in our papers, if we ever use Gauss, we always say what it is in Tesla.
Uh-huh. Okay.
But anyway, the answer is I don't know. What I can tell you is, because you see, in a sense, what we're really talking about is what is the product of the charge and the magnetic field. And you say, okay, let me just make it an electron charge and tell me what it is. The important thing is, I mean, I'm sure we could do that. It's just that I haven't done it, so and I wish I could give you the answer. But here's what's important. What's important is how big is the field compared to a field that's interesting on some level of what you would like to simulate. Let's say the field that you would need to see the quantum Hall effect or the fractional quantum Hall effect. And the answer is we're not there yet by a long shot. Mm-hmm. And what is the biggest field that we can get? We think we can get a field big enough to do that, but how would we do it? There is a physical limitation to how big the vector potential can be. So that's perhaps the more important thing. The vector potential can never be bigger than, remember, charge times vector potential is momentum. That product of charge times vector potential can never be bigger than 2 photon momenta in this picture. Now, if I used a different structure where I had more sublevels, I could increase that by a factor of maybe 2 or 3. But that's it. It's going to be a few times the momentum of a photon is the maximum vector potential that I can have. Now, magnetic field is gradient of vector potential. It's actually curl, but it has the units of space derivative of vector potential. So what's the smallest distance over which I can make this happen? Well, you know, it's going to be a few microns. That's the smallest size I'm going to be able to make a cloud. So that's the answer, but I wish I could give it to you in Gauss, but I just can't.
Well, so the real answer is that the field is just right for seeing the interesting physics you're looking at
except
now.
this isn't the quantum Hall effect. This is a
No.
long way. So we've
But-
seen the classical Hall effect, but that's pretty easy. But so we have to do a lot of work before we're going to be there for the quantum Hall effect.
Mm-hmm.
So somebody has to decide whether we can keep going, because of course we're past the time.
I think we can have the questions later in the break. Yeah, let's continue. Let's thank Bill again.